Welcome back to another explainer. Look, if you've ever tried to manage multiple AI agents, you already know the drill. It usually ends in total, absolute chaos. But today we're looking at something that actually fixes this. We're going to break down how the mission's multi-agent framework functions. And spoiler alert, it's way less like a simple, easily confused chatbot and way more like a highly efficient software factory floor. Let's get right into it.
Okay, so we've got to start by talking about the core issue that's limiting developers right now. Because honestly, the bottleneck in software engineering, it's no longer intelligence. Today's AI models are incredibly smart. The real problem is human bandwidth. I mean, even the absolute best engineers simply do not have the attention span to supervise 50 different tasks or features all at once. Every single task requires your attention, and every code commit requires your review. So the hard truth? We are the bottleneck here.
But imagine for a second, what if you could just hand off the actual implementation? Picture stepping away while agents work for hours, or maybe even days, entirely on their own. You get to act as the visionary. You decide the what, and this multi-agent system just takes over the meticulous, grinding how. That is the dream, right?
So here's our roadmap for this explainer. We're going to cover the human attention bottleneck, the three-role architecture, adversarial testing, serial execution, mission control, and we'll wrap it up with a real-world Slack clone case study.
Section 1. The human attention bottleneck. We are the limit.
You know, when most people think of AI agents, they usually picture a single, easily distracted chat session. But a mission is an entirely different beast. It's a full ecosystem of agents. It combines delegation, verification, broadcasting of shared states, and negotiation all into one package. By relying on really structured handoffs between these specialized agents, the system can pull off incredibly complex, long-running tasks without drifting off course or just forgetting the original goal halfway through.
Section 2. The three-role agent architecture. Separation of concerns.
Now, the absolute crucial point of this architecture is its three-role separation of concerns. You can think of it exactly like a construction site. First up, you have the orchestrator. This is your foreman, the one who plans the project and maps out the big strategy. Then you've got the worker. This is the specialized tradesperson who actually implements the processes and writes the code with zero distractions. And finally, the validator steps in. This is the ruthless QA inspector who verifies everything end to end. And trust me, they do not care about the worker's feelings. This separation is vital because it ensures nobody is grading their own homework, which, let's be honest, is a massive problem in simpler agent setups.
So here's how it actually plays out. Before a single line of code is even written, the orchestrator drafts what's called a validation contract. This contract defines exactly what done means. Because of this upfront work, the worker inherits a completely clean slate. No accumulated baggage, no degraded attention from the planning phase. They just read the spec and start building. Once it's built, the validator steps in to conduct the testing. And the beauty here, the validator knows exactly what to test, all thanks to that initial contract.
All right, Section 3. Traditional versus adversarial testing. Testing that actually works.
There is a really stark difference in the testing mentality here. If you've ever dealt with traditional unit testing in AI coding, you know the frustration. Usually an AI writes a feature, writes some tests for it, and then proudly claims, hey, 100% coverage. But those tests are totally biased. They're just confirming the AI's own potentially buggy decisions. Missions, on the other hand, use end-to-end behavioral validation. The user testing validator hasn't even seen the code. It acts completely adversarially. It spins up the live application and literally fills out forms and clicks buttons exactly like a real human user would. It doesn't care how the underlying code looks, it only cares if the thing actually works.
Moving to Section 4, Why Serial Execution Wins. Sequential consistency. You might be thinking, let's just throw 10 agents at the codebase at once. But parallel execution creates absolute chaos in software development. Having multiple parallel agents means they're stepping on each other's toes, duplicating work, overwriting state, and creating absolute nightmare merge conflicts. The coordination overhead totally destroys any speed gains you thought you had. Instead, missions use serial execution with targeted parallelization. They restrict writing code to just one serial worker at a time, but, and this is a big but, they safely parallelize the read-only tasks, so you can have agents simultaneously searching the codebase, researching APIs, or doing code review. Sure, it might seem a little slower on paper, but over a multi-day sprint, the error rate drops dramatically and correctness actually starts to compound.
Section 5. Mission Control and Tracking. Track asynchronously.
So if these agents are grinding away for days, how do you track them without losing your mind? Well, the framework uses a mission control interface that fundamentally changes how you handle long-running projects. Step 1, you literally just converse with the orchestrator to scope the goal. Step 2, you approve the plan. Step 3, you track progress asynchronously. You get these structured handoff summaries detailing exactly what the active worker just finished and any issues they found. And Step 4, well, you literally step away. You can oversee the project as a manager from a distance or simply let the factory hum while you go hang out with friends. Now, a massive part of managing this factory floor involves a pretty cool skill called droid whispering. Because its whole architecture is model agnostic, you aren't locked into one specific AI provider, you just have to put the right model in the right seat. For planning, you want slow, careful reasoning models. Implementation, that needs fast, highly creative coding models. And for validation, you need precise, ruthless instruction-following models. By mixing and matching these, you easily compensate for any individual model's weaknesses and make sure your factory is operating at absolute peak efficiency. Okay, Section 6. Building a Slack clone. Let's look at a real-world example.
To really ground this, let's look at what happened when the system was tasked with building a complex, real-world Slack clone completely from scratch. The implementation workers handled the heavy lifting, as you'd expect. They consumed 60% of both the mission's total wall clock time and the token usage. The remaining 40% was dedicated to planning, validation, and overhead. It's actually a remarkably balanced distribution of labor that perfectly mirrors how a highly functional human engineering team operates.
But here is a completely wild, surprising fact from this project. Validation literally never succeeds on the first go. Never. Every single time the validator finds a bug, an unrendered page, or a broken button, and that forces the orchestrator to go back and scope out corrective work. But honestly, this proves exactly why this adversarial QA loop is absolutely critical. Without it, the system would just confidently ship broken software. With it, the system actually self-heals.
And the results really do speak for themselves. By the end of those continuous self-healing QA loops, 50% of the final lines of code in the Slack clone were actually tests. This resulted in an unbelievable 90% behavioral test coverage for the finished application. You end up with a code base that is cleaner, safer, and way more robust than when you started.
So I'll leave you with this provocative thought. AI models are only going to get more specialized and capable. The raw intelligence is already there. So the real question is, are you building the connective tissue, the structured handoffs, the roles, the ecosystem to actually orchestrate them? Or are you still bottlenecked by your own attention, trying to manually review every single line of code? Now that we have the blueprint for autonomous software factories, it might finally be time to let the system figure out the how while you get to focus on the what. Thanks so much for joining me on this explainer, and keep innovating.